All right, so using our activity there that you see on Desmos, we're going to be answering a number of questions about the velocity of this object as it's traveling upwards and then falling back down. Now, when I talk about velocity, y'all know what I'm talking about, right? Most are going to say yes. If not, here's a little quick idea about velocity. And yes, if you're just now taking physics, you're going to be spending a lot of time with velocity this year. Velocity is just a fancy name for speed. The difference is that speed is always a positive number, whereas velocity can be positive or negative. So velocity really just represents the rate at which whatever it is changing. So the very first thing we want to do is we want to figure out the average velocity of this object from t equals 0 to t equals 2.5. All right, so in order to be able to find this average velocity, basically I need to know what the velocity is at the start and the end. So what is the velocity? Let's write it over here like this. What is the velocity at 0? Well, that's probably not the right question, right? Because do we know the velocity at 0? No. Okay, well then what do we know at 0? Yeah, what it's actually telling us then is the height at 0. Okay, so that's what we can know then. Okay, so then I got the height at 0, and I know that's 0 based on the picture, right? The other thing I need to know then is what it is at 2.5. So we're going to have to get the height at 2.5. Yeah, it's a nice, conveniently pretty number of 100. All right, so now we can actually figure out velocity, because velocity is like speed, right? So like in this kind of a case, I don't think the picture says it's actually in feet. I don't know if it says it or not, but it'd be like the height in feet. And the time it says is in seconds. So we're going to end up with something that's like feet per second, right? So that means we need to know how many feet did it travel and how many seconds did it take to do it. Well, if I want to know how many feet it traveled, I would do like the 100 minus 0 to know how far it traveled, right? And to know how long it took, I'd have to do the 2.5 minus the 0 for the time that I started out. Well, of course, this particular one gives us nice, pretty numbers, 100 over 2.5. And now we can actually do that calculation, and it gives us 40. 40 what again? What are our units on that 40? That is feet per second, yes. Because that 100 on the top represents the feet. The 2.5 on the bottom represents the number of seconds. Does the math that we just did look familiar? It should. Because the math that we just did is the slope formula. When we found the average velocity, basically what we did is we found the slope between 2 points on some function. Now we don't know the actual function that's going on behind the scenes that would represent this height function. But we just did find the slope between 2 points on it. And actually, technically, it's the slope of the secant line even. So now to practice it, I'd like you to please find the average velocity of the object from t equals 2.5 to t equals 5. You'll notice that you're having to go back to the demonstration on Desmos, move it around so you can see what those actual numbers are, and then use those. So the data we end up using is that at 2.5 we have a height of 100. Of course, we knew that from the last one. And at 5 seconds, we have a height of 0. All right, and so then we can go ahead and plug that into our slope function, basically. Now, when you plug it into the slope function, did you pay attention to the order? Because you'll notice in this case, you might have been looking at it and thinking originally, well, these numbers are exactly the same, so I'm going to get an answer of 40 again. But we don't quite. We actually get an answer of negative 40 feet per second here. Remember, that's one difference between velocity and speed. Velocity can be negative. Because what this is telling us is happening is that this object is falling, it's actually moving downward at a speed of 40 feet per second over that period at least, over that as an average. All right, now then, what would the average velocity of this object be from t equals 2 to t equals 3? All right, so when we do the math on this one, you find that at h of 2 and h of 3 both of those have a height of 96 feet there. And so when I put this in the slope function then, and actually figure out the average velocity, notice it gives 0 feet per second. Does that mean that between 2 and 3 seconds that the thing did not move at all? No, I mean, you can even see where it's moving up at like 2.5 seconds. It's even higher than that, right? So this is what average velocity does. Average velocity can tell us like just between the endpoints what's happening. Again, think of like the secant line. This is telling us that if I was looking at a graph, that it's just horizontal between any 2 points. That's all. It's just between those 2 points. It doesn't tell me what all is going on in between where it goes up and goes back down and all that stuff. And so that's one of the ways that we're going to be extending this today, is eventually we're going to be looking at how we can get more detail. But average velocity gives us certain advantages and certain disadvantages. And a lot of it's in this example here, where you can see that we can figure out that it didn't really move between these. It didn't change position between them. But we can see that, well, yeah, it didn't move at the endpoints, but it did move in between. So let's look and see what did happen more in between there. Please find the average velocity now between t equals 2 and t equals 2.5. All right, so when we do that, thankfully we probably didn't have to mess around with the picture this time to get our values, since we had worked with h of 2 and h of 2.5 already. So we use the 96 and the 100, do the math out, you find out that it's going to be 8 feet per second. So this is already telling us a little bit more about what's happening between them, right? So that's a little bit more detail. For a lot of things that we might be looking at, this would be a little bit more useful. Now, does this still tell us the actual velocity at t equals 2 or at t equals 2.5? No, it's still just an average between them. Now, there's only half a second between these 2 points, but it still isn't telling us the entire picture, right? So then that's what we need to figure out. How would we figure out the velocity of this object at a specific time? Well, let's start by looking at t equals 2.5, because this one we can kind of reason our way through. What do you think the velocity would be at 2.5? Excellent. Yeah, the velocity at 2.5 would have to be 0, because we were going up and then it peaks out right at 2.5 and then it starts going down again. This really is kind of a parabolic motion, and you'll see that actually quadratics do end up being involved when you deal with this stuff in physics if you haven't yet. And so that really is kind of the peak. So we can know then that the velocity at 2.5 would be 0, just by kind of thinking that through. Well, that one, it's logical, right? Let's do something a little more challenging now. What is the velocity at t equals 2? This one's going to take you a little bit longer to kind of work through. So I'm going to give you here a few minutes. Go through and figure out how would you figure out what the velocity is exactly at 2. All right, so what he did there, he said that he basically found h of 1 and h of 3 and used those values to try to figure out what the slope was, what the average velocity was between those two. Since 2's right in the middle, you notice we're hoping that would actually give it to us. And in this case, we ended up with an answer of, you said 16 feet per second. Okay, cool. Let's get another one. All right, so that one actually is a very similar method, right? There you did h of 1.5 and h of 2.5, you said. Okay. And that one also gave us 16 feet per second. Okay. That's looking pretty good, at least. That's a good hint, because we're getting the same thing for both, so that's good to see. All right, so another one there is you use the h of 2. Why am I writing that in red? That's because I wanted it to look different. I'll use black, because red has bad connotation. H of 2 and we did h of 2.5, and you saw that at h of 2 it was at 96. 2.5 was 4 more than that, so you said you got an answer of 4, was it? Okay. Because it went up by 4 over that half second. That would be feet per second. All right, good. All right, so it seems like we actually have some good ideas going on here. Now, between these, we kind of have two different sets of methods, as it turns out here. In the blue, we have picking one point on either side and getting the slope that way. And in the black, we have using our actual number as one of the points, and then using one of the points on the side of that. Are both of those going to be valid? I mean, would both of those make sense as possible ways to approach it? Or can we say that it has to be this or that? All right, so I want to see what you can do with these ideas. So taking the stuff we just talked about, take one of those methods, and please use that method to figure out what would it be at t equals 4? What would the velocity be at the moment of t equals 4? All right, so you now had some time to work through this one, and maybe after the last one you're kind of given a pointer, you're given some direction about something to try. So let's see, what did you end up getting on this one? All right, so you said you found the slope between 3.5 and 4, and what was that one? All right, so you got negative 40 there, and then you went to the h of 4 and the h of 4.5 and figured out the slope between those two. Okay, and so that was negative 56. And then you said you then took those two and averaged those two. Trying to get even more precision here. Okay, so what is it on one side? What is it on the other side? Average the two out. And when you averaged it, what did you get here? Negative 48. Okay, negative 48 feet per second. Cool. Again, a slightly different tactic that we can take on it, right? All right, so another method is we can again just choose one on each side, right? And so if I take the h of 3.5, h of 4.5, use those numbers there, I end up with an answer of negative 48 feet per second. So notice that both of these methods, different methods, they both still got us to the same answer. That's cool. I like seeing that. And yes, both of these are valid ways to approach it, and these can get us to the right answer here. Now, on these so far, we've had to basically take a point on either side, right? Because we figure, well, it's going to be right between. But what if I want to know the velocity at t equals 0? Take a moment, think about what would you get as an answer from this one? Right, now I'm guessing that most of you right now are saying, well, I can't go into the negatives because my information doesn't give me the negatives. All I have is 0, so I can at least use that. So I can figure out, okay, what's the h of 0, and then go to the closest thing after that, which I think most people would say is at 0.5, and we could take those. Well, h of 0 is at 0, h of 0.5 is at 36. If I then find the average velocity between those, 36 to 0 over half a second, that's 72 feet per second, which is getting close actually to what it could correctly be. But what I want to do is I want to now push you to get even closer than that. How can you get an even more accurate number than that? Let's check an idea here. To get a more accurate estimate, could I use h of 0 and h of 1? So h of 1 gives me 64. If I then found the average velocity between those two, that would be 64 feet per second. Which one of those two numbers do you think is more accurate to the velocity just at 0? So I heard 72 because this distance between our times is less. Okay, so it sounds like we agree with that idea. So if that's the case, then I wouldn't want to go bigger here. Instead, I'd want to go smaller, right? So I'd want to go to h of, what's a smaller number that I could try plugging in here? Okay, 0.05. I just heard that one. Try that. All right, so then at 0.05, I end up with 3.96 for my height. Well, calculate the slope from that. What would the slope be between 0 and 0.05? All right, and so when we do that calculation, we end up with 79.2 feet per second. Does it seem like that's going to be the exact number? Do you think that actually at 0 that's going to be 79.2? No. Can we get even closer then?
0.01.
Yeah, we could try an even closer number, right? Like I just heard h of 0.01. Okay, let's try that one. What would that give us for our slope? All right, so for that one, when I plug 0.01 in on the Desmos, I end up finding out that we're now at a height of 0.7984 feet. Well, I'm then going to divide that by the 0.01, because of course it's just the distance from 0, right? And so it's 0.01 away, and so that gives me 79.84 feet per second. Do you think that's going to be the exact number, the exact velocity at 0? No, even that doesn't seem exact, does it? So we've been going through this kind of progression here. We started at 72, that was half a second away. Then we went to 79.2, that was 0.05 seconds away. Then we went 79.84 when it was just 0.01 seconds away. Any ideas on what you think this is probably approaching? What do you think that the actual number probably is based on that information?
80.
Yeah, I'm hearing a lot of 80s, right? It looks like it's approaching 80 feet per second. The question is it actually? Well, the good news is there's ways we can actually answer that question. There are ways that we can actually find out that exact value. But right now, the only way we can do it is keep trying to make that number smaller and smaller. As a little side note, digging a little deeper in something that we're going to get into a lot later on as well. What formula do we normally use when we're trying to find the slope between 2 points? More particularly, the slope of the secant line. Yes, the difference quotient. And so, like, really, we could actually think of this. I'm not going to go into the full thing of this here, but we could actually think of this just as a difference quotient problem. But I want to focus in on one particular part. As I've been going through this progression, you know, you see those green arrows there leading us along as we got closer and closer. What were we doing to the value of h as we got closer and closer to our point? What was the h getting closer to? The h was getting closer and closer to 0. So we could actually talk about the h approaching 0. And what we're going to be really looking at here today is how what we're trying to find out is what limit would that reach? Because there would be like a limit to just how far it could go, right? Because like these numbers are getting bigger, but they're only going to get so big. They're going to hit a certain limit, and that's the number that we're looking for. Well, today is actually about limits, because we could write the limit like this. We're looking at the limit as h approaches 0 of the difference quotient. And so anytime you're getting closer and closer to a value, you're dealing with a limit. Now, this is the limit notation and the definition. We're going to be making use of this today, so please go ahead and put this into your notes. And then we're going to play with our limits a little bit graphically. And then we'll come back to the whole slope idea after we've gotten used to the limit notation a little bit more. And so in these notes, we have a new notation where we can actually write something like this, where we write LIM for limit, and then underneath that, we have the x right arrow n. Now, these can change as you're going to see. This doesn't always have to be x. This is just going to be whatever the variable is in our function. So it could be as t approaches a number, or as h approaches a number. And n is always just going to be some number. You know, we're using the traditional thing where n just represents a constant number there. And so we'll always be talking about approaching some number there. And then we write our function. And so this is a fairly common notation that you're going to be seeing come up here, especially as we start really launching into seeing what happens with some of those slopes as we get closer and closer. For the moment though, let's take a look at this particular graph. Now I'm going to use this graph for multiple sets of problems here right in a row. So if you want to take a moment and copy the graph down so you have something to look back at, you're welcome to. And then after I've given you time to do that, we'll go through and we'll figure out how we would find each of these limits that you see there down the left-hand side. All right, so we're now going to figure out what each of these limits would be given the graph. Now, just to be super clear, this graph is the graph of f of x, which is why we're using f of x there as part of our limit. All right, so the first question is we want to know what the limit is as x is approaching 3, but notice that 3, it's like to the power of negative. What this means is that limit as x approaches 3 from the negative side, which we would tend to say as x approaches 3 from the left. All right, so that's what that's really meaning as we take a look at that notation. Now, that could be a good thing to make note of, like when you wrote down the problem. You might want to write a note to yourself. That means as x approaches 3 from the left, so that you remember that piece. So what that means then is that I have the point 3 right here, and I'm looking to see that as I'm going along this graph from the left-hand side, and I'm approaching 3, what am I getting really close to as I get really close to 3? What's the y value? It's 2. Yep. And so in this case, the limit as x approaches 3 from the left side is 2. All right, now we do the next one, which is the limit as x approaches 3 from the right side. And so you notice I start on the right side, I'm just following the graph along. Now as I get really close to 3, what is this graph approaching? And again, from the right-hand side, so as I get along here, what am I approaching? Which y value? 2. And so this one is also 2. All right, now when you then see this one here, where we say the limit as x approaches just 3, you notice in this case there's no plus or minus here. So it's not saying whether we're going from the left or the right. That's because this is from both sides. So when it does not have like to the power of negative, to the power of the plus looking thing there, what it's saying is it has to be the limit from both sides. So then visually what I'm doing is I'm saying as I come from the left and as I come from the right, what am I approaching? In this case, they're both approaching the same thing, right? They're both approaching 2. And I know that, of course, because I just did them up here. And so then my answer here is 2. In order for me to be able to actually answer that one, I had to be able to know the limit from the left and the right to be the same. And we'll see some examples where that may not be the case later. And then the last one, we don't want to forget about the function notation, just what's the value. What is the value of f of 3? So when I go over to 3, what's the actual y value? 2. This is a fairly common type of problem where you'd be finding a limit where it's just part of a normal continuous function that we would see. But most of the questions you'll be asked about limits won't be the nice common type of function. They're going to be these piecewise, and we're going to be looking to see what happens at a trickier point, like 4 in this case. You're going to see one of those things does change a little bit as we go and answer these questions. All right, so for that first one, we're looking for the limit as x is approaching 4 from the left side. So I'm following my graph along, and I just go up until I reach 4. Now, as I'm approaching 4 from the left side here, what height am I approaching?
4.
4, yep, because I'm approaching this y value up here. So this one will equal 4. What about from the right side? So as I'm approaching this from the right side, what number am I approaching? 4. Again, I'm approaching a y value of 4. Now, was it the same from both the left and the right? Yes. That means that that's what the actual limit is at 4 itself. Not just from the left to the right, but the actual limit at 4 then is 4. All right, so then what's f of 4 for this problem?
4.
It's not 4. Because you'll notice right here at 4, there's an open dot, which means there is no value at 4. So there's no solution there. If you were doing this like on a wall map, you would type in DNE because it does not exist. And that can often happen because you'll notice, even though there's no value at 4, we were able to figure out the limits. And this is one of the things limits can do for us, is it can tell us, well, where would that value be? Even though it doesn't exist, where would it have been if it did exist? All right, now with that in mind, let's do one last set of questions based off of the same graph. So take a moment, write down these new questions, then again start thinking through how you'd answer them. All right, so for the first one, we're looking for the limit as x approaches 2 from the left side. So as I'm moving in from the left-hand side and approaching 2, what value am I approaching as I come along here? 3. Yep, looks like I'm approaching a y value of 3 there. So that's going to approach 3. Next problem, as x approaches 2 from the right side. So I'm following the graph from the right until I hit 2. What value am I approaching in this case? Yep, I'm approaching a y value there of 1. All right, now was it the same from both the left and the right? No. That means that the limit just at x equals 2, without it specifying left or right, the limit just as 2 then does not exist. There is no limit specifically at 2 because it's different from both sides. Okay, well, can we know what f of 2 is then? Well, is there a solid dot at 2? Yes, there is. So notice, I have that solid dot up there. Of course, the open one is down here, but the solid one is what I care about. F of 2 is where that solid dot is, and so the answer for f of 2 would be 3. Notice that the actual function value doesn't have to be these. It doesn't have to be the same as them. Now, in this case, it was the same as one of them, but you'll even see situations where it isn't even that, where all 3 of these can be the same, but this can still be different. And I'll let you kind of start bending your brain around what that might look like.